Okay, this is a video that goes over the lesson done on January 25th, 2013, when there was a 2-hour early dismissal for our afternoon classes. So this is the warm-up, so please pause the video and work on the warm-up, and in a moment I'm going to just start working on it myself and talking you through it. Okay, number 1 says evaluate the expression without a calculator. I have a 4 in the denominator of my exponent and a 3 in the numerator. That means I'm taking the 4th root of 16, and then I'm going to raise that answer to the 3rd power. Well, the 4th root of 16 is 2, and 2 to the 3rd is 8. So the answer is 8. Number 2, it has a negative exponent. That means it's going to be 1 over the square root of 25 to the 3rd. Well, the square root of 25 is 5, and 5 to the 3rd is 125. Okay. Number 3. I want you to notice that number 3 and number 4 look different. That's because they are different. Number 3 does not have parentheses around the number with the negative sign, but number 4 does. Watch how I rewrite each one. Number 3 gets rewritten as negative the 5th root of 32 to the 4th. But number 6 gets rewritten as the 3rd root of negative 8 squared. Do you see the difference here? The negative is outside the root and the power, and here the negative is inside the root and the power. So, returning to number 3, the 5th root of 32 is 2, 2 to the 4th is 16, and then this negative makes it a negative 16. For number 4, the cube root of negative 8 is negative 2, and then negative 2 squared is 4. Number 5, to solve this equation, we're going to divide by 2, and that gives us x squared equals 6. I'm going to take the square root of both sides, and because the square root is an even root, it's going to be x equals plus or minus 6. Number 6, I'm going to take the cube root of both sides. Because it's an odd root, I don't have to worry about plus or minus, and I've got x plus 3 equals the cube root of 14.
Miss Silver, could you come to the main office?
So now we've got x plus 3 equals the cube root of 14. We're going to subtract 3 from both sides, and that gives us x equals negative 3 plus the cube root of 14. Here are the homework answers from last night. Take a moment and check your work. I did number 24, as you can see, for another class, and in a moment I'm going to scroll. Why don't you pause the video? In a moment I'm going to scroll down and talk about number 33. Okay, so number 33, here are the 4 expressions, A, B, C, and D. So you can see when I evaluate the A, C, and D, my final answer is what I started with. 2, 2, 2, 2. But when you look at letter B has an answer of 2, but inside those parentheses was a negative 2. So the nth root of a to the n equals a works for everything except for negative numbers, I should say, for a, and using even roots and power. So this is the only situation where that does not work. Okay, today's lesson is about 2 things. It's about simplifying radicals, and it's also about looking for like radicals. Okay, yesterday we talked about multiplying and dividing radical expressions and expressions with rational exponents. Today we are going to continue that by really making sure our answers are simplified completely. We have 2 goals in simplifying radicals. The first is that there are no radicals in the denominator. The second is that we want to remove any perfect nth powers. What that means is if I have a perfect square and it's a square root, I need to take out that perfect square. If I have a cube root, I need to take out any perfect cubes. If I have a 4th root, I need to take out any perfect 4ths. So here we go. Write the expression in simplest form. assume all variables are positive. We don't have any variables, so it doesn't really matter. I have the cube root of 2,000. So the first thing I'm going to do is I'm going to break this down into prime factors. And 2,000 is even, so I'm going to break it down into 2 and 1,000. Well, I immediately see 1,000, and I'm thinking about cube roots, and I'm like, wait a minute, 1,000 is like 10 times 10 times 10. So I can rewrite the cube root of 1,000, or of 2,000 as 2 times. And just like with simplifying a perfect square, here's my perfect cube. The cube root of 1,000 is 10, so it comes outside the radical, and the 2 is remaining inside the radical. So my final answer is 10 times the cube root of 2. Letter B, the fourth root of 96. I'm going to start the same way. I'm going to divide out 2, and that leaves me with 48. And 8 also is divisible by 2, and that would give me 24, which is also divisible by 2, and that gives me 12. And that's also divisible by 2, and that gives me 6. Now, yeah, 6 is 2 times 3, but I don't really need that, and here's why. I have the fourth root of 96. That's 1, 2, 3, 4, 5 2s. Ooh, what the heck? Active slate went crazy. 1, 2, 3, 4, 5 2s, and a 3. We are looking for perfect fourths. So I see I have 4 2s. That means the fourth root of these 4 2s comes out as a 2. And what's remaining, 2 times 3, stays underneath. So I have 2 times the fourth root of 6 for letter B. Letter C is the cube root of 32. Take a moment and try this one by yourself. Pause the video. Okay, so I'm going to start the same way. 32 is even, so I've got 2 times 16, and then 16 is 2 times 8. Now, there are 2 ways to continue. The first is to recognize, hey, guess what? 8 is a perfect cube, and take that out. The other way is to just continue by listing out prime factors. 2 times 4, and that's 2 times 2. So that's going to be the third root of 1, 2, 3, 4, 5. It's perfect cubes, so here's a perfect cube right here. It comes out as a 2. The cube root of 2 times 2 times 2 is 2. Third root of, and then this stays inside as 4. Okay, letter D is a fraction, and so what we need to be concerned about here is the denominator. We're going to start reducing every fraction by listing out its prime factors. We're just going to do it a little neater, not in the tree form we did A, B, and C. So I'm going to list out, obviously 25 is going to be 5 times 5. $12 is going to be 2 times 6, and 6 is 2 times 3. Well, I can see that the numerator does not reduce at all, but the denominator I need to rationalize. And to rationalize the denominator, that means there can't be any radicals there. It has to be a rational number, a whole number. I have a cube root. That means I need 3, just like in letter C, 3 of the same number. I have 2 5s. So I think to myself, if I need 3 and I have 2, how many am I short? Well, I'm short 1. So I'm going to multiply by the equivalent of 1. I'm going to multiply by third root of 5 over the third root of 5. I'm only going to do this step next once. That gives me in the numerator 2 times 2 times 3 times 5. And then the denominator will be the third root of 5 times 5 times 5. Well, the cube root of 5 times 5 times 5 is just 5. The cube root of 2 times 2 times 3 times 5 doesn't reduce, so we're just going to have the cube root of, this is 4 and this is 15, that makes it 60. We have 3 more we're going to do. we've got the fifth root of 1/8. So the first thing I'm going to do is write that as 1 over 2 times 2 times 2. Write out the prime factors. Now, this is a fifth root. That means I need 5 of the same numbers. I have 1, 2, 3. That means I need 2 more. So I'm going to multiply by the fifth root of 2 times 2 over the fifth root of 2 times 2, because that would divide out to be 1. In the numerator, that's going to give us the fifth root of 4. And in the denominator, well, now that I have 5 2's, the fifth root of 2 times 2 times 2 times 2 times 2 is 2. Go ahead and pause the video. I'm going to slide this down in a second, and try F and G on your own. Okay, letter F is the fourth root of 2/9. I'm going to rewrite that as the fourth root of 2 over 3 times 3. Well, it's the fourth root, and I only have 2 3's. That means I need 2 more 3's. Oop. So the denominator will just become 3, and the numerator will be the fourth root of 2 times 3 times 3, which is 18. And for letter G, I've got the fourth root of 48 over 25. So we're going to make that 2, and that would be 24, and now it's 12. So wait, 24, 12, 6, 3. There we go. All over 5 times 5. Well, again, this is a fourth root. I need 4 to make a perfect fourth. I have 2. I need 2 more for a perfect fourth. So I'm going to go 5 times 5 over the fourth root of 5 times 5, because this all divides out to be 1. So my denominator is just going to be 5. When I look at the numerator, I notice this is the fourth root, and I have 4 2's. I'm going to take the 2 out, so it goes in front of the radical. And inside the radical, I'm going to have 3 times 5 times 5, which is like 3 times 25, which is 75 inside the radical. Okay, the next thing we're going to do is we are going to look at adding and subtracting radicals. Now, before we look at any of these examples, I want to think about this. If I had x plus x squared, I can't add those together. They aren't like terms. They have the same base. You know, they both have x as the base, but they don't have the same power. In order for things to be alike, like terms, they have to have the same base and the same power. If I put a 2 here, it's not the same power. If I put a 2 here, it is. To add 2x squared and x squared, I really am just adding the coefficients, right? 2 plus 1 would give me 3x squareds. Keep that in mind for a second. As we look at A, we have this very complicated looking expression. We have 4 times 3x to the 1/3 minus 2 times 3x to the 1/3. I have 4 3x to the 1/3 minus 2 3x to the 1/3. They have the same base, and they have the same power. So all we're going to do is say, okay, 4 of them minus 2 of them equals 2 of them. I'm not going to do anything with the 3 to the 1/3. That's the type of term I have. Just like over here, I didn't do anything with the x squareds. 2 of them plus 1 of them made 3 of them. When we look at B, they have the same kind of radical, which means they have the same exponent, but they don't have the same base. But 27, we know, is 9 times 3. So that means it's 3 root 3. Now, 12 is 4 times 3. So that's like plus 2 root 3. Now they have the same base and the same power. So I can add them together and get, what was that? And get 5 root 3. Letter C, they're already the same base and the same type of radical, the same exponent, so I can add 1 plus 4 and get 5 times the 3rd root of y. Go ahead and pause the video and try the next 3 on your own. Okay, letter D, we have 2 5 root 3's minus 1 5 root 3's, and that leaves us with 1 5 root 3. You don't really need the 1. Here I've got 7 2 to the 1/8 plus 4 2 to the 1/8 makes 11 times 2 to the 1/8. Letter F, we have 4 root x plus 2 root x makes 6 root x. Oops. Okay, so right now what I would like you to do is pause the video and work on 7.2 practice A, which is, as you can see, part of your homework. In a minute, I'm going to kind of go through some of the ones that I went through in class that people had asked about, and then go ahead and work on page 14. I'm going to turn the page in a little when I'm done talking about this worksheet so you can see what the answers are for this. I want to point out that there is a second worksheet right after 7.2a that you can use to study for the exit ticket. There's a separate video for this if you want to see how to do these problems. For those people who did not get to see this live and in person, remember you will get priority at lunch on Monday with questions. So go ahead and get started. Pause the video. Okay, the first 12 problems, guys, are all problems that kind of deal with what we did yesterday. Just looking, here we have the same bases, but different exponents, so we're going to add them, because those are the properties of rational exponents. Just like if you had x squared times x to the third, we would add the powers and get x to the fifth. Here we're going to add the powers and get 4 to the 5/3. Number 2, we're going to multiply the powers, because raise a power to another power. 3/4 times 1/3 would be 6 to the 1/4. Number 3, the only thing you can do is make that 15 to the 2/3. Kind of a dumb question. Same thing, number 4, all you can do is make it 13 to the 5/4 under 1. 5 is a little more interesting. You can subtract those. We're not going to divide and subtract. The bases are the same, so we don't touch. Subtract the exponents, you get 1/6. I don't really know what you can do to number 6 other than make it 2 to the 1/8 over 3 to the 1/8. It's kind of a silly problem. All right, so 7 through 12, we want to see what they have that's the same. Again, here, number 7, they both are square roots. Because they have the same type of radical, we can multiply the bases. Number 8, we have 2 radicals operating on the same base. So what I'm going to do is I'm going to rewrite those radicals as exponents. So I have 5 to the 1/3, all to the 1/2. So that's like a square root and a cube root. When I raise a power to another power, I multiply the powers. That gives me 5 to the 1/6, which is the 6th root of 5. Number 9, they're both square roots, so I divide 20 by 5, and I get the square root of 4, which is 2. Number 10, I can just take the square root of 1 and take the square root of 25. Number 11, as you can guess, works a lot like number 8. It's going to be 3 to the 1/2 to the 1/5. Well, 1/2 times 1/5 is 1/10, which would be the 10th root of 3. Number 12 looks really scary, but if you can just imagine this, these are all square roots. So it's just going to be the square root of 6 times 30 over 10. Well, let's see. 30 divided by 10 is just 3. 6 times 3 is 18. The square root of 18 reduces, because it's 9 times 2, to 3 root 2. Simplify the expression. Assume all variables are positive. Again, all we're going to do is apply the laws of exponents. Number 13, we add. So we have x to the 3/4. Number 14, we multiply. So let's see, 2/3 times 4 would be 8/3. Again, we multiply, except the 3 and the 6 cancel. The 6 becomes a 2. 2 times 5 is going to be x to the 1/10. There's really nothing you can do here. I mean, I guess you could write it 3 to the 1/2 x to the 1/2. And here, though, you can take the cube root of 27 for number 17 and get 3x to the 1/3. Number 18, I'm not even going to waste the space on the board because it's just going to be 1 over x to the 7/2. 19 and 20 are kind of nice. They are both subtracting the exponents because the bases are the same. And here we have x to the 3/3. Well, 3/3 is just 1, so it's just x. Here we've got 1/2 minus 5/2, which would be negative 4/2, which is the same thing as negative 2, which is 1 over x squared. Number 21, again, kind of like the others. I'm not really sure what they want, like 16 and 17. I mean, the square root of 100 is just 10, and the square root of x is the square root of x. Don't worry about rationalizing that quite yet. 22, these are all, it's kind of nice, these are all like terms. Every problem of these 6 is a set of like terms. So we've got 6 root 3, we've got 2 root 7, 15 times the 5th root of 22, negative 5 root x, negative 3 the 3rd root of x, and 2 times the 4th root of x. Here are the answers to tonight's homework, which would be to finish that if you didn't finish that completely. They did reduce some of these. They reduced 20. Oh, we didn't do 20. I was like, what? We didn't do that one. Here are the answers for page 414. And here are the answers for the rational exponents worksheet. Again, this video is on my YouTube page. Please see me if you have any questions.